Today, we're pulling back the curtain on a piece of Java that's always there, working in the shadows, the hidden superclass, java.lang.Object. Every single Java developer uses it every day, but not everyone really gets how to make it work for them. So let's dive in.
It's a pretty wild thought, isn't it? You can write a class in Java that is completely, totally empty. But somehow, it's not really empty. It's already got functionality baked right in. How is that possible? Where do those methods come from?
Well, that's exactly what we're going to figure out. We're going to demystify this whole thing by looking at the object class. You'll see how methods you've probably heard of, like toString-O, equals-O, and hashCode-O, are really the invisible foundation of everything you build in Java.
Okay, so the answer to our little puzzle lies with one single, all-powerful class that is, quite literally, the ancestor of every other class in the entire Java universe.
And here it is, the object class. It's the root of the whole family tree. So every single class you write, it doesn't matter if you type extends object or not, it automatically implicitly inherits from it. It's like getting a free starter pack of essential methods. Let's make this real with a super simple example. Here's a student class. It's about as basic as it gets. It just has a name and a constructor to set that name. And notice, we haven't told it to extend anything at all.
And yet, just because it's a Java class, our simple student class instantly has access to all of these powerful methods. We didn't write them, but they're there, ready to go. So let's take a closer look at a few of the most important ones and see what they actually do.
First up, let's talk about turning our objects into something we can actually read. That's what the toString method is for. The problem is, its default behavior is, well, it's pretty much useless for debugging or, anything. So let's say we create a new student object, we'll call him John, and we try to print it to the console. What do you think is going to pop out? His name, maybe? Let's see.
Yeah, not quite. What we get is the class name, an @ symbol, and then this hexadecimal number. This is the object's hash code, which is basically a fancy way of identifying its location in memory. This is what the default toString from the object class gives you. It's not wrong, but it tells us absolutely nothing useful about our student.
Clearly, this won't do. We need a better way. So how can we get a readable, actually useful string representation of our object? The solution is to override the toString method. We're basically telling Java, hey, ignore that default version from the object class. From now on, when someone asks for a string version of a student, use this one instead. Here, we're just returning a simple string that actually includes the student's name. And just look at the difference. Now when we print the object, we get our custom human readable output. It's a night and day improvement, and all we had to do was take control from the default object behavior.
All right, let's move on to an even bigger idea, equality. When are two objects really the same? The equals method has a very specific answer to that question by default.
So the default equals method that we inherit from object is super strict. It only cares about one thing, identity. It's basically the same as using the double equals operator. It asks, are these two variables pointing to the exact same spot in memory? And this leads us to a classic problem. Let's say we create two separate student objects, S1 and S2. Now, logically to us, they represent the same person. They're both named John. But what does the default equals method think? It returns false. And you might be thinking, why? It's because S1 and S2 are two different objects, living in two different spots in memory, even though the data inside them, the name, is identical. The default behavior doesn't care about their content, only their address. You guessed it, the solution is to override again. We write our own equals method to tell Java what equality should mean for a student. In our case, we're saying two students are equal if and only if their names are the same. Now we're comparing their actual state, not just their memory location. And now, when we run that same comparison, we get true. Finally, we've successfully defined what it means for two student objects to be logically equal, which is almost always what you actually want.
But be very careful. Overriding equals comes with a huge responsibility. And this brings us to the most critical and honestly, the most often misunderstood part of this whole topic, the unbreakable contract between equals code and hash code.
This right here is the golden rule. It comes straight from the official Java documentation, and it's not a suggestion, it's a contract. It means that if s1.equals s2 is true, then s1.hashCode must be equal to s2.hashCode, no exceptions.
And breaking this contract is the source of some of the most frustrating bugs you'll ever encounter in Java. Why? Because collections like HashMap and HashSet rely on this rule to work correctly. A hashmap uses hashCode to figure out which bucket to put your object in, and then it uses equals to find it inside that bucket. If two equal objects have different hashcodes, the hashmap will look in the wrong bucket, and your object will seem to just disappear.
Okay, let's wrap this all up and make sure these key ideas really stick. The object class gives us a starting point, but the real power comes from knowing when and how you need to step in and take control.
So here are the 4 big takeaways. First, everything in Java inherits from object. Second, override toString to make your life easier when you're debugging. Third, override equals to define what sameness means for your objects. And finally, the most important one, whenever you override equals, you must also override hashcode. They're a package deal. Don't separate them.
You know, understanding the object class really peels back a layer of Java that's always there, but you might not always see it. And it makes you wonder, what other fundamental rules and hidden behaviors are quietly shaping the way your code runs every single day?